Okay, so we're going to talk about a new kind of integral now. We've laid the groundwork. We've talked about vector fields, and we're going to motivate this new kind of integral with a physics problem. The physics problem involves work. Y'all remember work, I'm sure, from chapter 1. We talked about work. We refined the formula for work, in fact, using vectors. This is one of our sort of motivating examples for vectors and dot products. Okay, so we're going to define a new kind of an integral, and very importantly, I just want to give you the warning. This is not going to be just like all the other integrals we've seen. I mean, a common sort of, device that I've been using is, hey, every integral that we encounter, it's all the same, right? Single variable integrals are just like double integrals, which are just like triple integrals, which really, as you get right down to it, are kind of just like scalar line integrals, and they're just like the scalar surface integrals. It's always chop it up, add it up, and it's always the same, right? So there is going to be something significantly different here. It's still going to be mostly the same, but anyway, heads up to notice something very importantly different. So here's the problem that we're going to address. I suppose that I'm at this point A, and I want to get to this point B. How much work does it take to move from A to B? Now, your first reaction might be, oh, well, yeah, you look displacement dot force. That was our big, revision of high school notions of work, is that it's a dot product. After all, displacement is a vector, not a scalar. Force is a vector, not a scalar. And the dot product accounts for directions and everything. So here, though, let's make the problem harder. What if I'm not moving straight from A to B? If I could draw a straight line. I am going to specifically be moving along that curve. Right? So, now, does that matter? Does it make any difference? Oh, a little uncomfortable if you think about it. Right? Okay, furthermore, the force is not constant. Let's suppose, and notice here, the force vector at this point is like that, but the force vector at that point is really different. Right? So clearly I can no longer just say, look at the displacement and dot the force. The force isn't the same everywhere. Furthermore, that dot product formula doesn't in any way recognize that I'm going along that specific curve and not just straight line. Right? So what we have here is a harder problem. I'm going to approach this problem with a kind of an eye towards, let's create an integral. Chop it up, add it up. And the first appeal that I will make is that the total amount of force, the total amount of work that I exert is the sum of the amount of work that I exert across each of these individual pieces. So if I compute the amount of work that it takes to move that one little piece, and then add how much work did it take to move this next little bit, and then how much work did it take to move the next little bit? So you add those up, and it should give me the total amount of work. So said differently, I argue that work in this scenario is an accumulating quantity, right? Kind of like mass. Now, it's not a physical stuff like mass, but it has this feature of accumulation in that, when you chop it up in little pieces, and look, how much gas do I burn? Right? Leave it that way. The total amount of gas that I would burn driving along this path with a car is, how much gas did I burn in the first little bit? How much gas did I burn in the second little bit? Clearly, the grand total amount of gas burned is the sum of how much gas did I burn in each particular step. And this lecture will be highly outdated in a few years when all cars are electric. Right? Oh well. Okay. So let's look at individual pieces, and let's ask the question, on this little piece of curve, how much work does it take for me to move along that little piece of curve? Well, it's not exactly a straight line, but you know what? Since I'm looking at little small pieces of curve, and especially keep in mind, we're eventually going to be taking a limit. And in the limit, these little pieces get straighter and straighter, flatter and flatter. Right? We can make a reasonable approximation that our displacement is a straight line. We're said differently that displacement is represented by a straight vector. Yeah. Now, furthermore, the vector field is still not exactly constant, right? The vector field here and the vector field here, they might be a little different, maybe, a little bit, but again, increasingly small. As we slice increasingly small, you expect that over the course of this curve, it should be approximately constant. Not exactly, but again, in the limit, round off errors, hopefully, we expect, go away. Okay. So that's the big idea. Now, notice that I do have this arrow pointing, which you might call the wrong way. The field vectors F are like this. Now, this is just a quick annoyance in physics, and it's something everybody has to be aware of. So heads up. But this pen right now that I'm holding up in the air, there are actually two forces. Right? Gravity is pulling it down, right? So the force is down, but yeah, the thing is it's not falling, right? Now why isn't it falling? Well, because I am applying a force up, right? And they are exactly opposite forces because those two forces add up to zero. It has to add up to zero, otherwise F equals ma, the pen would be accelerating. And it's not accelerating, it's just sitting there, right? So you got to keep this in mind. There are two forces in play, and you have to decide which one is the one that is relevant to what you're doing, right? So if the question says, I force, there is a force acting on the pen, they give you that force. And then if they say, how much force do you apply? Well, that's the negative. Right? And that's the circumstance that we're in here. The presumption was that this vector field that I have in red here is representing the force that is, that we are resisting. That this is the sort of the external force being applied, and that we are moving contrary to that. So the amount of force that I have to apply myself is exactly the opposite of the force that I am trying to overcome. Okay, how are we doing? Is everybody on board? Okay. Okay, so on that little piece of curve then, the negative of the field vector, the negative of the force field vector, dot my displacement vector, that dot product would be my estimate of how much work did it take to move across this one little piece of curve. Right, so purple dot orange gives me work. Delta W on that little piece. So let's come back up here to our development. We're trying to figure out the grand total amount of work. We're going to compute that as a sum of little pieces of work. Sure does look familiar here. Right, we've done this a million times. I just made the argument that displacement dot force, don't forget the minus sign, is what computes each one of those little pieces of work. Right? And so these little pieces of work add up over all the pieces. And we have here a formula for, our estimate of, how much work should it take. And notice it kind of looks like a Riemann sum. Everybody good so far? You see, we chop it up, look on each little piece, you write down the formula, and then you add them up. Okay. And here you can already see the difference happening. Right? Very importantly, in this summation that I've got written down here, I don't have something multiplied by size exactly. right? This isn't something times delta S. It's not something times length. And it's just unavoidably, and very importantly, work is not just something you multiply something times distance. Right? It is a dot product. It's intrinsically, the work related to moving a certain distance depends on how that distance, how is that displacement oriented. It would be harder to move that way because you're moving directly into the wind, as it were, directly against the force. Same distance, it would be much easier to move that way. Because there you're going perpendicular and you hardly even feel it. This is different. Yeah? Okay. Another thing, as promised, another big difference is that notice that this thing here, that's not a scalar valued function. This is a vector field. The thing that's, cosmetically at least, the thing that is in the place where, I would have expected my integrand to show up. It's a different kind of a critter than we've seen previously in that ball. Okay. And then, of course, lastly, not only is this differently a vector, and this is differently a vector, notice as well, not for nothing, that is a dot product. And dot products are not the same as just, times. Right? So there's several, this is, come on, pen. There are several eyebrow raisers in that expression. Something a little different. Okay. And yet this is the result of a chop it up, add it up sort of approach to the problem. So anyway, what we're going to do is we're going to call this a new kind of an integral. This thing here, this expression where you have, it's a limit of a sum, as usual. There's kind of a something times something, but importantly, it's a dot product of two vectors instead of a scalar product of two scalars. The vector on the right is not exactly size per our pattern, but it is it's not unrelated, right? If you think about it, this vector it's representing both the size and the orientation, if you will, of that little piece of curve. The magnitude of this is the size, right? So it's size and then some. It's more than just the size. So anyway, lots to keep track of, but this structure we're going to call an integral. No surprises. dx to represent the delta x, the displacement. Right? That's our displacement differential. I'm going to call it an integrand. Again, even though it's a little different, but that thing there, of course, the integrand you represent by throwing it in there. Now, we can't forget about the fact that, look, this is in fact a dot product, right? That matters. I'm going to put that in the notation there as well then. Right? So you can't just write f vector of x and then just write dx, right? You've got to put that dot in there as a recognition that there's a dot there. And that's important. And then again, chop it up, add it up. So we are in fact adding up over all the pieces of curve. A curve is one dimensional. We're adding up with this. There's a single index that indicates where are you along the curve, and so we're going to represent that with a single integral symbol. As we always do, the domain, whatever this curve is, subscript of the integral symbol, and we've got ourselves a notation. This again, if following our patterns, this is very natural notation for this thing. Also, lastly, terminology. This thing is an integral over a curve. And I remind you, we've already seen an integral over a curve. Right? We talked about scalar line integrals Friday. Integral over a curve. And at the time I made the observation that, okay, there's going to be another kind of an integral. It's also kind of it's similar. It's also over a curve. Scalar line integrals, though, We called them scalar line integrals because they were just like every other integral we'd seen. The differential was size. It was ds. The integrand was a scalar, just like every other integral we've ever seen. Right? So this is the different kind of a line integral. I feel like I have to call this a line integral because we are just, like previously, we are adding up over a curve. It is still added up on a curve. But because of the big differences that we're seeing, I don't want to give this the same name that I give, what we eventually call scalar line integral. So this is what I like to call a vector line integral. Right? Both line integrals, but the vector prefix there intended to emphasize the differences. The differential is a vector. The integrand is a vector. Okay. Let me pause on that. Anybody have any questions about that? Does everybody algebraically see the difference, the structural differences between scalar line integrals, familiar old friends, and vector line integrals, brand new, still have an eyebrow slightly raised over this thing? Okay, everybody's good? Okay. All right. Oh, just a little preparation for life. Unfortunately, both of these things in common practice are routinely referred to as just line integrals. And it always bugs me because, okay, come on, these are pretty different things. Now, in defense of this terminology of just calling both vector line integrals, scalar line integrals, calling them both line integrals, there's never any actual ambiguity, because if you say, hey, look at the following line integral, right? There is it's perfectly clear. You see the dot product right there, right? This could not possibly be anything other than clearly it's a vector line integral, right? So it's not that that's a problem, but it makes me happier to give the distinction to remove the confusion. Okay. Certainly as you're first learning the material, I think there's value in emphasizing that this is a different thing. Okay, enough of that. Okay, so with this notation defined, notice that the formula that we had up above was for computing work. Well, work is just this integral. What we are integrating, notice, is got a minus sign in it. That minus sign is in recognition of the fact that the force that we are pushing with is the opposite of the force that is while we are pushing. Okay? It's opposite of the force that we're overcoming. Okay. Alrighty. So, new kind of integral. Next question, how do we compute it? Now, reminder, how did we compute scalar line integrals? We decided we didn't like the domain. We viewed the domain as an image. We did a pullback. Details follow. How did we compute scalar surface integrals? We decided we didn't like the domain. We viewed it as an image, parametrizing again, and we did a pullback, and more details followed. Okay, so here we are again. How do we compute this kind of an integral? I don't like this domain. This domain is dimensionally awkward. It's a one-dimensional thing, namely a curve, but it lives in a three-dimensional world. I'm going to view it as an image, right? And I'm going to pull back. So I'm going to try to figure out how to represent this curve as being the image of something that I like better. Oh, wait. We just got through doing that Friday, right? This is, in fact, still the same kind of curve that we were previously looking at. The domain itself is not different. It's the structure of the algebra, the structure of the Riemann sum that's different, right? But it's still a curve in space. And just like I had it with when I was studying scalar line integrals. I don't like this domain. I'm going to parameterize in exactly the same way. I'm going to pull back and still hope to get an integral on the t-axis. And it's really a pretty familiar situation. In fact, a lot of our setup that we previously created is still here and useful. So previously we talked about dt on the t-axis, and that corresponds to a little piece of curve there. And we talked further about the associated vector, the dx vector. That dx vector is what I like to call the position differential. Here's our position, x, right? And differential means when you change t by some amount dt, what is our linear estimate of how position changes? Well, that's exactly what dx is. Yeah, the actual change in position is a little off because it's curving, right? But this is the differential of our position. So position differential, I think, makes a lot of sense. Furthermore, we have a formula for computing dx. We did this last time. Dx is v dt. Again, old news. Go a few sections back to the section on scalar line integrals. You'll find dx is v dt. Okay. So we're actually in really good shape at this point. So parameterize. Dx is v dt. Now, there's a temptation to look at this picture and say, okay, well, the big trick with pullbacks is that I've got to look at that size and that size, and I need to know how those sizes are different. I need to know the stretching factor between, how big is that piece of curve and how big is that little piece of curve. And there's a temptation to say, well, I guess we better get down to it and compute that stretching factor. Every other pullback we've done, we had to compute a stretching factor. But here's the thing. Every other pullback we've done, we needed to know ds, or we needed to know the size over here in some form or another. In this case, we don't need to know how big that little piece of curve is. We need to know something arguably more complicated, namely the position differential, dx, namely whose length is the magnitude, is the size, and whose, but also has a direction. But the thing is, we already have dx. Right? So I don't need to compute ds. It's not part of the algebra that I'm looking at. I mean, let's look at the thing that we're trying to deal with. This Riemann sum I want to rewrite. No ds's. I don't need ds. I just need dx. And dx is here, and here's the formula for it, and we're actually done. Right? So the weird thing about computing vector line integrals is that pullback scenario, everything that we needed for a successful pullback, through a parametrization was already stuff we'd already established. We've already established that curves are images of parameterization. We've already established that the vector representing the differential of that displacement is called dx. We've already established how to compute dx. End of story. So, so here's how it all comes together. Very conveniently, this vector line integral that we want to compute. dx, that dx is, as established previously, v dt. I don't need to insert a stretching factor because I'm not computing ds. I don't need to compute ds. I already have dx. How are we doing? Is everybody on board? This used to weird me out. When I got it in my head early on that when you do a pullback, you got to insert a stretching factor. That's the deal. That's the cost. right? You got to pay the price if you want to capitalize on the advantages of doing a pullback. And here, you kind of, I mean, I guess maybe in a way you kind of do. I mean, I did have to convert. I couldn't just erase where it said dx, just erase that and write dt instead, right? So that's true. Okay, I did, but there was no actual stretching factor, scalar stretching factor involved. Or you might say, said differently, that stretching factor, that scalar stretching factor is part of this velocity vector. If you prefer, that's another way to think about it. Okay. So, just rewrite everything in terms of the parametrization. Note that x is, of course, a function of t. That's your parametrization. And off you go. We have now successfully converted a vector line integral into a Calc 1 single variable integral. Okay. I'm going to do several examples here. Does anyone have any questions, though, first? Everybody okay? Okay. Okay, here we go. Okay, so we're going to compute the amount of work that it takes. Okay, right off the bat, we're computing a work. We know work is a chop it up, add it up, but more specifically, work is computed as a vector line integral. Okay, the amount of work that it takes to walk along a certain path, and there's a certain force given to us. Okay, well, the path, counterclockwise along the unit circle from there to there. That path is our curve, which we parametrize. Yep. Okay. Now, y'all remember parametrizing. Again, every curve's a little bit different, but the unit circle, we have a convenient, you might say, standard parametrization of the unit circle. This is going counterclockwise. Oh, good. This parametrization is going counterclockwise. Just what we wanted. These points 1, 0 and negative 1, 0. Where's my? Here we go. 1, 0 is where I start. This is where t is equal to 0, and in that parameterization, we get around over to here where t is equal to pi. Okay, so t goes from 0 to pi. Is everybody happy with where the parametrization came from? Okay. Okay, next, let's talk about the integrand real quick. You do always have to worry about the, wait a second, do I need to stick a minus sign in there? Physics, again, has this annoying feature of, wait a minute, are they telling me this force, or are they telling me this force? Which one is it? So it's all in the phrasing of the question, or in interpreting the question. This says about the wind that the wind necessitates pushing with an opposing force of capital F. That's telling you that the force that I am pushing with is capital F as given. So it does not say the wind applies a force to you of capital F. I would then have to oppose that by pushing negative F. Okay. So the way this is phrased, the given here is just then that it is in fact F that is our integrand field. Is everybody on board? Okay. All right. Okay, so it's a plug and chug. F is given, and F is identified, and C is parametrized, and our formula up here says in order to turn the line integral into a single variable calculus integral, I've got to compute the velocity vector, and then I've got to plug in the parametrization. Well, the velocity vector is just taking a derivative. Derivatives are computed component-wise, right? Chapter 3. So here's your velocity vector. And notice that is going to show up as we rewrite our ds. Let's see here.
our dx. So there's our dx.
VDT.
And v, which is x prime, is that.
Just plugging in.
Now don't forget we have to plug in the parametrization itself for our x.
So the parameterization is x is cosine t comma sine t. Now what we are plugging that parameterization into is our vector field. Let me come back up here real quick. Our vector field f is negative y comma x. Okay, so we're going to be composing, right, our vector field f negative y comma x. So don't forget, x is cosine t. Y is sine t. So negative y is negative sine t. Comma x, well, x is cosine t. Everybody happy? Okay.
So just plugging in, and conveniently this works out to be a nice little integral. It's just integral of 1, as it turns out. That's how this dot product works out. Dot product is just 1. And easy integral, answer is pi.
Everybody happy? Okay.
There's something else that I'd like to comment on real quick. Not only was it easier, sort of mysteriously easier for us to develop the formula for how to compute vector line integrals. I mean, everything was already done. We'd already developed dx. We'd already found a formula for it, VDT. In fact, we went even further and computed ds. We don't even need the ds here, right? So it was oddly easy for us to develop this formula for vector line integrals, even though it's a more sophisticated concept. And that's strange, right? Normally, sophisticated concepts are hard to deal with. Unsophisticated concepts are easy to deal with. You know, it's strange that didn't happen. But here's another, again, counterintuitive, unexpected convenience. And that is, not only was it relatively easy to develop this formula, it is relatively easy to deal with this formula. Notice in this formula, yeah, you've got to compute the velocity, and that's a derivative, but that's easy. Right? But you don't have to compute the magnitude of it. And if you think about it, that's where a lot of the pain of computing scalar line integrals is that, you know, when you compute that velocity, when you take the magnitude to get your speed, that is your stretching factor, that magnitude involves square roots. And so the ugliness that seeps its way into your integral when you're doing scalar line integrals very often comes from that square root. Here, no square root because no magnitude. Right? And notice, no square roots showed up in this calculation. So, again, it's such a wonderful little bit of good news. We're taking a more sophisticated concept here, right? This Riemann sum that we wrote down, this is a more sophisticated construction, but the development of how to deal with the resulting integral is an easier development with an easier to deal with resulting formula. So, I mean, that's, you know, good news. Sometimes stuff works out. Okay, let's do another example. This is a very similar example. We are still going to be going counterclockwise, unit circle 1, 0 to negative 1, 0. So same path, same, therefore, parametrization.
Right.
Okay. This time, though, the wind necessitates pushing with an opposing force. Okay, so the F that's given here is our integrand. The only difference in this question is that we have a different formula for our vector field. So this is no longer negative y comma x. Now it's x comma y. So a lot of this question is going to be very similar. I mean, we do have, after all, the exact same curve So exact same parameterization. No surprise, of course, it's got the exact same velocity vector. Right? So that's pretty much the same going on there. So that's the same, that's the same. We are still plugging in the same parameterization into the vector field because we are still going along that same curve. Again, the only difference is now we have a different vector field. Here, f of x comma y is x comma y. Different vector field. Yeah.
What would the parameterization look like if we were going clockwise?
Yeah, great question. Let me do that in a couple seconds. Yeah, fantastic question. So on this particular one, though, notice we're on different little sort of detail here. We end up with a dot product that is exactly 0, and so therefore this integral turns out to be 0. So that's nice. Again, every so often you get lucky. Physical plausibility. This is a picture. It looks like a picture of a sunrise or a sunset, depending on your mood, I guess. If you're an early riser, this is a sunrise. This is a picture of what the forces look like along this, along your process of moving along this path. And as you move along the path, notice that wherever you might happen to be, you are always moving perpendicular to the forces. So not only should you, of course, get 0, but you can see that we're getting 0 as a total because, furthermore, we are adding up a bunch of zeros. These dot products are all individually all 0. Okay. All right, so that's kind of a plausible, I think, plausible result here. Okay. Okay, so great question she asks. What if we were going the other way? Now, let me see if I recall here. No, I don't have any other. Okay, so yeah, let me parameterize this curve the other way, and let me look for the best. I think I have a little bit more room to work with here. So let's suppose we wanted to start there and move like that. Okay, so I'm going to give you two different ways to think about this. Take your preference. One way to think about this is that this curve, where we start there and move like that, as compared to this curve where we start there and move like that, which, by the way, I know how to do, right? This curve here is cosine t sine t. Right? Notice that the curve that I am now interested in is a reflection of that. It's a reflection over the y-axis. See what I'm saying? So that means that I can write down the formula for this green curve by just saying, okay, well, what do I do to these points? I've got these points cosine t, sine t. What happens when I reflect over the y-axis? Well, the y-coordinates stay the same, right? And the x-coordinates just, I stick on a minus sign out of the x-coordinates. So, negative cosine t, sine t. Everybody happy with that? So that'd be one way to do it. Here's a different way to do it with different pros and cons. Another way to do it would be to say, okay, I'm going to draw t explicitly on the picture. Let's see here. I'd like to, okay, suppose that I am here. And suppose that I wanted this to be where t is equal to 0. Then t is now this angle. Right? You can see that as desired, that's where t is equal to 0. And this over here is where t is equal to pi now. Now, it's not theta. Right? Theta's polar coordinates are still polar coordinates. But I'm just defining my parameter t to not be theta. I'm defining my t to be something that's convenient for my purposes for this curve. Is everybody on board so far? So if I define t to be that angle, then t equals 0, and the t increases, and then t becomes pi, clockwise as I wanted it to be. Okay, so how do I then describe the coordinates of this point here? Well, that point, theta, is pi minus t. And this point is still, in fact, cosine theta comma sine theta. Right? This is the unit circle. So I would write that point then as cosine theta sine theta, which I would then have to recognize, okay, well, yeah, but theta is pi minus t. And then you'd have to use your angle addition formulas. Or remember, by the way, I encourage y'all to remember there's a lot of symmetries of sine and cosine functions and all the trig functions. It's a pretty good idea to make sure that you're very comfortable with how to think through the various symmetries of sine and cosine. So you can argue directly, just from that point of view, how these rewrite in terms of cosine t and sine t. And it'll give you the same answer. So, okay. Either of these is fine. Is everybody happy? Okay, one last quick example, and then let's see, how are we doing on time? Yeah, okay. We'll do this one last example. Yeah, so here, let's go counterclockwise along the unit circle from, now here, different starting point, different ending point anyway. We're starting at 1, 0, going to 0, 1. So we're only going a fourth of the way around the unit circle instead of a half. And that shows up in the parametrization. Still the unit circle, still counterclockwise. So there's our old friend, right? But now t goes from 0 to pi over 2. Yeah? Everybody good? Okay. This time necessitates pushing with an opposing force. Okay, so that means that F, again, is our integrand, no extra minus sign necessary. This time, the big difference is our vector field is 2, 5. So it's not negative y, x. It's not x, y. It's completely different at 2, 5. So look, everything else plays out just like it did before. We've got pretty similar parametrization. So we still have the same velocity, right? Just like we did before. We're still plugging in the same x of t, just like we did before. Big difference is, again, the vector field is now a different formula. We're plugging in cosine t, sine t into a different formula, a much easier formula, 2, 5. It's just 2, 5, independent of what you're plugging into it. So we get a different resulting integral. And this is, something that you can crank out, Calc 1 evaluation. Make sure you can do this, by the way. You can probably see this coming at this point, but we are going to have a lot of integrals in this class. And a lot of trig integrals specifically. And so make sure you're good at those. And that answer ends up being 3. Okay. Is everybody good? Question? There's a little bit to say here in the rest of this section, but we don't really have time, and I don't want to rush it. So we'll pick up here. I think we're page-wise. I think we're in good shape. So we'll call it a day here and pick up here on Tuesday. While I'm at it, let me also talk about the exam. So don't forget we have an exam Wednesday. Gosh, it comes fast. The fair game material for the exam, I don't think I'll include vector line integrals because we're not done with that today. And what's the rush? Okay, so we'll draw the line at section 5.10, which I guess was vector fields. And then tomorrow we are going to do new material. Tomorrow's Tuesday. We're doing new material tomorrow because we have to. We're pressed for time. The exam, however, will not cover any of that. But then again, the final exam, which is in a little over a week, which is horrifying, right? The final exam will cover tomorrow's material. So anyway. Okay, see y'all later. And I'll send out an email about all this.